Hi again, everyone. So let's continue, right? So first off, if you go to the ICTP-SAIFR web page, the course page, you see that we already have the video for the classes from the morning. And over here, if you look at attachment, you see? Attachment here. This attachment is a link to the notebook that we have seen earlier, right? Interesting thing is you don't have to, I saw someone taking pictures, right? So we will provide everything, right? So yeah, copy and paste works much better and just select the code and, you know. Well, the network's bad here. Oh, okay. That's not good, right? So, remember when I told you that that's the one issue with Collab, right? So if the network is not so great, then we have issues. So, of course, I have all of them downloaded here, but yeah. So this is the one for the first one, and right now we're going for the other one here, from class 2, right? That is right now, right? So this one here, and later on we'll have the exercises that are over here, okay? Okay, so I want everyone to open up your notebook. If people don't have notebooks, please follow together with someone who does, right? So you can, we haven't formed the groups yet, but you are already allowed to talk to people next to you. Right? Yes? Okay, so it's within the rules, okay? It's okay. Okay? So, okay, so let's go for this. So, here it is, second class. So, right now we are going to talk about something that is called bifurcation diagrams. Okay, so what does that mean, right? So, beforehand, we were saying, okay, I should probably do this, right? So, much better, right? Yeah? So, okay. And maybe increase the, is okay? Everyone can see? Well, if you don't see, you open up in your own computer, right? So it works. Okay. So, so the thing is, we build models, okay, and if we build a model, we want solutions. Sure, we now know how to find solutions, okay? Great. But the thing is, as you can already kind of guess from Roberto's class, right? So from this last class, many times we are not happy with a single solution, right? Because why? Because, well, we are not sure of the parameters, we are not sure even of when the time begins, what is the initial condition, we are not sure about a lot of stuff, right? So usually we don't have all the parameters, we don't have the initial conditions, we don't have, it takes a lot of effort to fully parameterize a model. That is, should have all the parameters, all the data, and so on. This is really rare, okay, really rare. So, so what do you do, right? So you want to get information from your model, okay? You want to get information from your model. So what you do from that is, usually you try to explore what happens for, at least for the parameters that you don't know. Some of them you usually know, right? So for instance, over time is kind of easy, right? So you just follow people along and see how long it takes you for them to recover, right? So this is easy. But beta, transmission rates and so on, this is usually very hard, okay? So most of the cases most of the times you don't have this kind of parameter, right? So you want to understand what happens in different situations, and you want to check what kinds of parameters will give rise to situations that resemble the data that you do have in terms of number of cases and so on. So you need to explore your model, okay? You need to explore your model. That is, you want to be able to say what happens for a range of parameters, okay? And this is what a bifurcation diagram does for us, okay? You want to run the model for set of parameters, a range of parameters, and see what happens, okay? This name comes from a specific thing that happens that is a bifurcation, but it's easier to show you than to tell you, okay? Yeah? Okay, so let's begin, right? So here I'm going to show you a more complicated model, okay? So Roberto is still in the SIR. We are moving forward already, okay? So we are going to talk about a similar model that is the SIRS model. Why is this less S here? There's no second S variable here. But this means that recovered people, you see that this is very similar to the SIR model, but there are two terms of extra here, right? So there's this guy here, oops, this guy here, and this guy here, yeah? What does this mean? It means that people that have recovered, that is, they are immune, they lose that immunity and become susceptible again, okay? So this is one way to model waning immunity or loss of immunity, right? So for instance, for influenza, right? So there are many strains of influenza, right? So what happens is not that you lose immunity, but every year you have new strains or new variations on the same virus. It's not the same virus anymore, right? Because it's a variation, right? But you do get the meaning, right? So yeah, you might. Now I know who the bio people are. Here I'm not talking anything completely wrong here, right? So it's kind of the same virus, but it's a different virus. So you're not immune to the new strains, okay? So in a sense, you are losing immunity because now the viruses are different, okay? Okay, so this is one way to do this, okay? So this is not necessarily something related to the individual itself, I don't know, losing its immunity, but the virus itself changes or something like that, okay? It's related, okay? Okay, so we have an extra parameter now, that is omega, okay? And two new terms, okay? What happens with this kind of model, right? What do we expect without solutions, okay? What do you expect? Can we eliminate the disease now? It's harder, right? If I have a peak and it goes down, but then susceptibles, all the recovered people eventually will become susceptible again. And then you have the condition for a new epidemic, yeah? So it may lead to a kind of, I don't know, some cycles or something like that, yeah? Maybe, yeah? Okay, so let's see, right? So first off, we have to solve this model, okay? So this is exactly like in the last class, okay? So this now the version with less comments, right? So the other version, I had comments explaining every single line. Now it's just the code, okay? So now I'm running from this time, beta, gamma, and omega over here, total population, and now again I have initial condition with the total population minus 1 initially susceptible, 1 infected, and now you see that this is, I probably should know this SIRS, right? But you see it's the same thing as before, but now I have this term here that is plus omega x2. x2 is the third element, okay? 0 is the first. And this term over here that is minus omega x2 over here, okay? And now I just call ODINT to solve the model, and then I plot the solutions, okay? And now let's hope the network will not let me down. Yeah. So the first time you run, when you open a notebook, the first cell that you run, usually it has to start up the kind of the machine, you know, like start up to import the libraries. So it always takes a little bit longer, okay? But here maybe it's also a network because it's all connecting. Oops. Okay, we have no network in this computer, so so fortunately I do have the notebooks here. So let me do it the old way, okay? Okay, so here we go. So I'm not going to run this into the... Are you guys with network over there? It's just me? Sorry? No network. IFT. Yeah. Yeah, I have the instructions here. I'm connected to IFT also, right?
If you have either room, then it's okay. So I will get to the computer guys to see if we can fix the problem.
Yeah. And also we should turn on the that one. Opa. Because I'm starting to get sweaty. Tá funcionando? Oh, it is working. Okay. So my plan was completely thwarted, right? So I wanted to get everyone doing it together with me, and now nobody can access anything, right? So yeah, okay. Well, I will just put the exercises on the board, yeah? Okay, so at least the classroom part I can do here, okay? So let's do for this.
Is there anything changing for you about the connections or still without connections? Eduron's working. But the IFT, because not everybody has Eduron. It's working now. It's not working. We have it in them. So auditorium is working, but it's usually very... Now it's okay? So you're usually... So is anybody without connected? Is anybody disconnected?
Yeah, here it's not working.
Is it working or
No,
working?
no, it's not. I'm connected at IFT and it's not working. So, okay, so let's do this over here. Okay. So now I'm running, now I'm running on this computer, okay, not on the network, but unfortunately you're not going to be able to follow, right? So to follow on your computers, right? And you have to do this later. But here it is. This is the same notebook, and now I have here the model that we were just talking about. Over here, you see the all media is shown, and all media is shown over here. And when I plot this, this is what I see. Okay, this is what I see. Let me just So, you see, this is what happens, and you see that at the beginning, at the very first peak, it looks more or less like SAIFR. But then, when it's going down, you see, when infections are going down, what happens is the recovered go down, because they are becoming susceptible again. You see? And since susceptibles are up again, then infections increase again. But now once infections increase, then susceptibles decrease again, and it kind of stabilizes to, what is this? This is not zero anymore, you see? It goes down to eventually becoming a recurring disease that is always at the same level of prevalence. Yeah? Interesting. Yeah, so it's, well, this model gives us this, right? So if you have waning immunity, if you have a loss of immunity, you may have solutions where the epidemic never goes away. You have an initial peak, and then it goes to a stable, this is called a fixed point, right? Or an equilibrium, okay? Equilibrium solution, where you go to a solution that is constant, okay? Okay, so what do I want with this model? Okay, I want to use it to see what happens when I change the value of beta. Okay, so what happens if I now try different values of the transmission rate, okay, the on-touch rate. Okay, so for instance, here I was using beta equals to 2, okay, beta equals to 2. Now I'm going to change a little bit, okay, 1.2. And now what happens? It's similar to the previous one, but now the infection is not 0 again, but is much smaller. Yeah? Okay. What happens if I go even lower here with beta? So let me just, to be sure, let me create a new cell down here. I think I have to plus here. Okay, so let me just print the last value of the solution, okay? So this is x minus 1. Oops. Oh. Here, you see, at the end here, I have, right, so divided by m. Okay, so you see that at the end here, I still have 1% of prevalence of the infections, okay? 1% versus 83% susceptible and 15% recovered, okay? But now if I reduce the value of beta, I say beta equals to 1, okay? What happens is that I don't have the disease, okay? I don't have the disease. So, well, this is exactly 1, maybe just to be sure, because Roberto said that R0 is never equal to 1, right? So we cannot, in the computer it can be exactly equal to 1, okay? In real life, it's complicated, but here you see that there's no disease anymore, right? So you see this is what 0 looks like in the computer, okay? Well, it's never exactly 0 either, but it's a very, very small number. So this is 10 to minus 7%, right? So it's yeah, so it's a very, very small number, okay? Okay, you see what happens here? It's like we had a fixed point, an equilibrium with disease, and when I change it beta, I no longer have the equilibrium with disease. So there's a kind of a changing behavior. Okay, as Roberto said earlier, the disease-free equilibrium, it becomes unstable when R0 is above 1. So this changing behavior of the model, this is what is called a bifurcation. Okay, this is what it means to what the word bifurcation means in this context. Okay, when you have solutions that are qualitatively different, right? It's not just that the infection, the level of infection is a little bit different. No, you go from no infection to some infection. Okay, so this is the fixed point, the disease-free equilibrium that was stable becomes unstable. Okay, so this is why this kind of plot is called a bifurcation diagram. Okay, but then it's kind of boring to keep changing beta, right? I want to do this in a way that I can see things more clearly, right? So what I'm going to do is I'll do this systematically. Okay, so how do I do that? I want to run several values of beta, okay? And for each of them, I'm going to look at the final solution, okay? After a long time, the final solution. Okay, pretty much like I just did with the final size of the epidemic. Okay, I run for several values of beta. So here I choose this range of betas here from 0.9 until 2, okay, with steps of 0.01. And I choose, again, you see this is a very large time. Why a very large time? Because I want to be sure that I already reached the equilibrium, right? There are no oscillations going on still and so on, okay? Now for each of those values of beta, right, I run the simulation again, you see, with now this beta here, inside here, right? It changes at every step of the loop, okay? And then at the end of the simulation, after the simulation, I add to this list of fixed points here, I append the last value, okay? So in Python, -1, when you use an index of -1, this is confusing for R people, right? Because -1 in R deletes that value, but in Python, negative indices count from the ending. Okay, so it starts counting, -1 is the last value, -2 is next to last, -3 is the one before that, and so on, right? So it counts from the end. So this is the last line, so the last time, and this second here is all columns, okay? All columns. When I do this, right, here, so what is the shape of this array fixed points here? For each beta, for each value of beta, I have 3 values, S, I, and R, and I have how many betas? This 110 here, right? So this is, I would probably print the thing itself here, right? So this is a very large amount of numbers here, and you see that here you have very small values, and then suddenly you have large values here in the recovered and in the infections, okay? So let me go back to what was before, just so it doesn't, yeah, okay, so let's plot the fixed points against beta, okay? This is it. So you see, I plot beta's fixed points, and here what it looks like, okay? So now, you see that for beta below 1, both R and I, they're both 0 at the end of the simulation, and susceptibles of course is 1, right? I should probably divide this by n, but you see that this is 1 times 10 to the 6, right? So this is this area, this is number of people, right? It's not proportions. And but then as I increase beta, it's a little tight here. Okay, as I increase beta here, I increase. You remember that we had oscillations, and then I go to a stable fixed point, right? What happens is that this increases a little bit, right? So I stop it at 2, okay? But what increases even more is the number of immune individuals at this stable point, okay? Nice, yeah? So this is this is what you do to have a feeling of what is going on with the model, okay? You start exploring parameters, okay? Good. So this is and the only bifurcation here is this point here. You see that when you look at the plot, is the point where there's a kind of discontinuity there, right? There's a beak over here, yeah? Yeah? Okay. Questions, people? Questions? Comments? So far, so good? Sorry? Oof. Even here, I can't hear you. Sorry. No. Oh, well, I'll repeat your question later. Yeah.
Can you give me an example of a disease that has this kind of behavior?
That doesn't have this. That does have what kind of behavior? Sorry.
Well, waning.
Ah, waning. Sorry.
The waning of immunity.
That you want an example of a system that does have
Yeah, because
waning immunity, but you know, influenza, right? I just told you there's. You know, of course, when I say waning immunity, it's complicated because waning here doesn't mean necessarily that you are losing cells from your body, like you are losing immune memory. It means that viruses or pathogens are evolving and escaping your immunity. You see what I mean? So influenza is the typical case. You can have the flu every year, right? So you lost your immunity from one year to the next. Right? Of course, if you had exactly the same strain from last year, you are immune to that strain. But next year it will be a different strain. Yeah? Now I don't know if is there some cases where you actually lose the immunity to that particular strain? I'm not sure.
it's because the model shows some behavior like is there a endemic behavior?
Mm-hmm. Yeah, this is endemic behavior, yeah.
But when we have some diseases that we have variants every year, it happens like
That they are seasonal in waves. Yeah, okay. What you want is not just waning immunity. You want to see waves. You want to see not waves. You want to see seasonality. You want to see. Okay. I will give you seasonality. Yeah, I will give you seasonality. Okay. Yeah, but that's true. Yeah. You can have malaria like 10 times. Yeah.
But I don't know the period, but it's very short.
Yeah.
Then next year you can be already.
Yeah. But it's not due only to evolving the parasite. Yeah. Yeah. Okay.
No two viruses are the same.
Yeah. Of course. Yeah. Okay. So. Here is pretty much the same plot again, right? But now I'm only plotting I, okay? I over M. And you see that this is the proportion of infectious individuals of the endemic equilibrium, right? Everybody heard this word endemic before. So an epidemic is something that comes, has a peak and goes, okay? Of course it can have multiple epidemic cycles, right? So epidemics every year. But endemic is something that is established in the population and is more or less there all the time, pretty much. Yeah? Is that a good enough definition? Yeah? It's not a definition, right? It's just kind of the idea of this stuff. Okay. Okay, so this is the proportion of infectious individuals. And you see that it's exactly here at beta equals to 1, right? That corresponds to when R0 is equal to 1, okay? Okay. There's something else that I want to show here, is that, okay, so it looks like changing beta from close to 1 to 2 here, doesn't make a lot of difference, right? I don't know. Of course, it goes from here from 1% of the population to 4% of the population. Yeah? So you say, well, going from beta of 1.2 to 2 is no big deal. But yeah or no? Looking at this plot, it doesn't look like that much of a big deal, right? Of course, you change the beta, you almost double the beta, but you only have a 4-time change in the proportion of cases, proportion of in the prevalence, yeah? Well, I see from your faces that you know this is a trick question, right? Yeah? You know that in your, yeah? Okay, I'm not fooling anyone. Okay, so what is the deal here? We have to be careful when we plot, we don't look at the solutions over time, because they may hide. If I just look at the final solution after a long time, we may be missing important stuff, okay? So it's not only the endemic phase that may interest us, right? So let me go back to the first plot over here, and let me but here, let me go to 1.2, it was like this, okay, 1.2, you see here. I think I will plot the proportion here, right? So just so we, over n, and this is now small s, small I, and small r. That is the proportion of each compartment over here, okay? And here it is. I don't like that I cannot quite, yeah, okay. Smaller font, but yeah, you see. So this is proportion, right? So you see that the peak here is close to 20%. And infectious is down here, okay? So it's very, very small over here, right? But if I change from beta from 1.2 to 2, you see, it's down here, right? The endemic equilibrium. But the peak is almost 20%, right? So when you change beta here, even though you didn't change much the equilibrium value down here, the peak became much, much larger of the first epidemic. Yeah, because actually what you have is, on the path to endemic, you have a series of peaks, okay? And the first peak is usually the largest one. So if you increase beta even more, this is even more dramatic, you see? So now it's, yeah, you see what I mean? So does that mean that bifurcation diagrams are useless? No, definitely not. But you have to be careful that you are not missing stuff, okay? So if you're interested not only on the endemic equilibrium, but this, I don't know, a newly arrived disease, and you are interested in what happens in that time frame where the disease first establishes itself in a certain region, okay? You are also interested in the initial peak of the disease, yeah? Yeah, sure. So, of course, you can do the same thing now. So instead of doing that, I can do something different. That is, I can look for the maximum value of the prevalence. Yeah. So instead of simulating and then only taking the last value, I can go here. I do exactly the same as before, but now instead of looking at the maximum value, I take the second column, that is prevalence, the I, and I look for the maximum value. Okay. What is the maximum value? It's where it reaches the highest peak. Yeah. And then I just save this into this array over here, and I plot it, okay? And this plot has a very different shape from the previous one, right? So you see that as I increase beta, the peak of the prevalence can go up to 15%, 16% of the population with beta equals to 2, right? So imagine if this were, I don't know, a severe disease, 16% of the population infectious at a single time, right? So this is catastrophic, right? So, yeah. Okay? You see the difference? So, yeah, nice. Okay. Now, yeah, this is, I think, yeah. No, I don't need this. Okay. So So now I'm going to give what he has, right? So I want to talk about what happens. It's morning, right? So let's see. Okay, I want to model seasonality. Okay, I want to model seasonality. So like flu. Okay, why does flu hit during the winter? Okay, in Brazil it's kind of weird, right? But in more temperate climates, people spend more times indoor during the winters, and they increase a lot the contact rates, and then it's easier to get infected during the winter because you actually have more contact, okay? Because you spend more time indoors, okay? In Brazil, this explanation is not quite so clear-cut, okay? But still, you can. There are other sources of explanation. For instance, if you have a drier climate, then the virus can survive longer in the air, and then it eases the spread and so on. Okay, so there are some rationales why we would expect transmissibility to be higher in winter than summer. Okay, let's assume that this is true. Okay, okay. How do you model that? How do you put into a model that beta is higher during the winter and lower during the summer? Sorry?
We will have to make an equation for beta, so
Yeah.
it will change.
Okay, so we have to make an equation for beta in such a way that beta changes over time. Okay? And if we are thinking about something that is recurrent, we want some periodic function. Beta is a periodic function, something that is up in the winter, down in the summer, and so on. Yeah? So, no thanks. Okay. Now I gave up on the natural. I don't want it. I don't want it anymore. Okay. So this is one way to do it. Okay. So this is a very simple function that is just beta of, now it's an explicit function of time. Okay. And now it's some average beta 0 here, and it has an amplitude of alpha and a period of t. Okay. This is a function that does that, right? So let's just, it's actually easier to run the code and plot this function here, right? So this is this function, okay? So you see here? So this is the function I just wrote here with an amplitude of 20% on prior to the average. The average is 2, and the period here is 52. I was probably thinking weeks, right? 52 weeks per year, okay? Yeah, so this is time in weeks, okay? And so this is winter, this is summer, and so on, okay? Good? Yeah, and you see that the minimum here is 2.4, maximum 2.4, minimum 1.6, right? So this is still transmissible. This is still, I don't know, R0 should be higher than 1 even during the winter the way it is, during the summer the way it is here, right? Questions, comments, disagreements? Yeah, it's time to complain about the model. Yeah, it's forced. Yeah. Yeah, but what is the option? Right? Because you want seasonality, but what induces seasonality, right? So we have seasonality like what we were discussing with measles, that is induced by generations, okay? New generations coming and they are more susceptible, and then you have peaks, okay? But this is probably not the case for flu. Probably not the case. It's not so simple to rule that out, but probably not the case. So, okay. So, what do we do? Well, we have a model. We want solutions, yeah? Yes? Okay. We have the model, we want solutions. So, let me increase again here. Okay, so what is the difference now? I have here beta 0, alpha, the period over here. And now you see that this t that was always here, now we are actually going to use t inside the model. You see? Now beta is beta 0 times 1 plus alpha times the sign of this guy here. Okay? That is exactly what I wrote over here. Okay? Yeah? Okay. Okay. And well, this means that at each point in time I'll have a different beta, and all the rest of the model is exactly the same. Okay? Okay. And now I run this model over here. Okay. And this is the solution. Okay. Oh. Yeah? Happy now? Yes? Seasonality, okay? And this is our urine. What is happening here, right? If I didn't have new susceptibles, if I didn't have waning immunity, this wouldn't work either, yeah? Because, for instance, if I go here and I say that, well, there's no waning immunity, right? That is, there's no term omega over here. If I put omega, it will shoot 0 over here, yeah? What happens? There's a peak, and then susceptibles go down, and then you don't have enough susceptibles to sustain transmission anymore. Yeah? You see? So you need waning, but you also need something else sometimes, okay? So let me go back there. So you need waning, but also seasonality is important in the transmission is important to keep these cycles going, yeah.
But in the case that we have a new serotype or variant occurring, would be more reasonable with the seasonality in the waning unit than the beta?
It's kind of weird, right? Because the waning immunity, that term over here, okay? Let's look at this term here, okay? This term over here, right? What happens if I didn't have any disease, right? So I have a bunch of recovered people and I don't have any infection anymore, okay? What happens with this term here, with this guy here? Oops, too much. With this guy over here, right? If I don't have any infections anymore, this is just exponential decay, okay? That means people are losing immunity at an exponential rate. So this is a process that is happening continuously, okay? So it's not a model for waning that is based on an event of a new strain emerging. It's more like, well, as time passes, there are new strains evolving, and you are more likely to be susceptible to some of them, just because evolution is always happening. So it's one way to think about it, okay? Of course, you can include in your model like but this is out of, you are no longer talking about ordinary differential equations. You have something like stochastic, new variants, and then you have an expected time until you are susceptible again or something like that, right? But it's harder to do that way, yeah. But in either case, you wouldn't expect this to be seasonal, right? Because this is the rate at which you lose immunity, right? So it's not like you're losing a lot of immunity during the summer and not losing immunity during the winter. You see what I mean? Yeah, so it would be really weird to say that omega is a periodic function of time. Yeah? Right? Okay. All you guys follow? Or anyone disagree? Objections? Yeah.
In winter, your system can be more inefficient because you are converting energy to heat, and your immunity decreases a little bit. I don't think it's
I don't follow how energy comes into.
When I'm in extreme freezing,
Okay.
you don't have energy to immunity. You have to just to survive, and your system converts energy for another systems.
you mean something like, well, if you have a very cold winter, then like human body has less immunity. Yeah, maybe for, I don't know, Stone Age, this would probably be true, but these days, right? So people live in heated places, right? So, you know, you only get cold if you want to go outside, right? So, yeah, I don't know. Maybe if there's a crisis of energy and so on, I don't know. But today, I don't think this is very reasonable, right? Yeah. Okay, more questions. More questions? Yeah.
Seems to me, maybe a misinterpretation.
Mm-hmm.
The infection curve drives the peak of infections, drives the peak of the susceptibles and
Yes, that's for sure. Yeah.
after this seems to invert, and the peak of susceptible in
Well, we can look at this, right? So we can plot both that were for beta and that were for infections together. Yeah? Yeah, and see if the peak of infections correspond to peaks of beta, yeah, of transmissibility, right? Yeah? So you see, there are questions about your model that, I don't know, you expect transmissibility to be strongly linked to increasing infections, but are you 100% sure? Right? So in the computer it's easy, right? You just make a new plot and you have all your questions solved, right? So let's make a new plot. I don't think I had plotted this before, right? So where is it? I didn't plot it, right? But then let's make a new cell over here. Okay. So what I'm going to do is I'm going to plot just, you see me here using the basic tool of computer science. You see here? And now I want this plot as well. But I just want to plot the number of, and I will do some trick here, do some trick here to have the same scale for two plots. Okay. Oops, but yeah, maybe put this one here in green. So you see, the blue line is infection, and the green line is transmissibility. So you see that when transmissibility picks up, then you see increasing infections. But by the time you get peak transmissibility, you are already falling in infections, right? Because you already have too many people recovered and so on. Huh? This didn't happen in the first peak. They are very close together in time, but later on you have more infections in the beginning rather than later in the season. Yeah? Interesting, right? Not obvious at all. I don't know. I don't think this is obvious, right? So, yeah? Nice? Nice, right? So this is nice. Okay. So, more questions. Okay, so let's move on here. Okay, so now I'm going to do something that is very, very funny, right? Especially for the physicists out there, right? So physicists, I've learned, they really like something called resonances. What is a resonance? Do everybody has some idea what is a resonance? Like when you have two notes playing close together and they become stronger and so on, yeah? Yes? Yeah, like music, you know, like when you play with, I don't know, your guitar and then you use the, what is the name of in English? Not the drums. The thing that you use to no, that you use to tune your guitar. You know, that always gives you the same. Yeah, exactly. Yeah, good. That thing. So the notes, if they are close together, they make they resonate together, you know, because they are very close together in frequency, okay? But here, you see, what does this have to do with epidemiology, right? So, yeah? So the thing is, you remember that this system, without the beta depending on t, was already kind of oscillating, right? Because if you go back up there, oof, where is it? Oh, no. No, this is, I know. Okay. Up there. You see the first solutions that we had here? Over here. Yeah, you see, they go, after a long time, they go to a fixed point. Okay. But they don't go directly there. They oscillate. You see? They oscillate, but the oscillations die out. Okay? What if the frequency of these oscillations are close to the frequency of the external oscillation, that is the frequency of the beta? Yeah? They can resonate together. Okay? And what do you expect when two frequencies interact and resonate together? You have larger amplitudes of the oscillations. Yeah? So this is what a physicist would tell you. Yeah? Okay. Okay, so does this work in epidemics too? Okay, let's see. So what I'm going to do, I'm going to do a special type of bifurcation diagram that is no longer called a bifurcation diagram. It's now called a resonance diagram. One thing to notice is that in this plot here, I no longer have actually a stable equilibrium. Okay, I always have oscillations because I have beta of t oscillating all the time. I have seasonality. Okay, how do I look at these solutions now? I will no longer look at the final state, right? Because it's here, but it would be here. It would be here. I don't know. I cannot characterize the final state of the system just by looking at the final point. Yeah. What do I have to do? I want to look at the minimum and maximum values. Okay? Not for the whole series, because I don't want to look at this minimum and maximum. I want the minimum and maximum only in a range after some time. Yeah? I'll look at the minimum and maximum. Okay? And with this, I can characterize the oscillations. Okay? The amplitude of the oscillations. Yes? Questions? Okay, so how do I do this? Simple. I go there. I will now vary the frequency. Okay, I will vary the frequency. Here I'm kind of varying the frequency of the beta function. Okay, but it's not very realistic. Okay, but I'm varying the frequency here for each frequency or each period. I'm going to solve the model again, and then what do? I make two lists now, right? I take the last 1,000 points of the plot. So I'm not looking at the whole time series. I'm looking only at the final part over here. Okay? Only at the final part over here. And I will take the minimum and the maximum. You see, I'm taking the minimum and the maximum. Okay? And now I can plot. Now let me run this in a moment. Yeah. And now I can plot this. Okay? So I will plot the minima and the maxima. You see, minimum and the maximum. I think this is only for I. Okay, this is the second column. Okay, for I. So this is the minimum and maximum of the infections, of the prevalence of infections, as a function of the period. Okay, and you see that if you are here, you have a much larger amplitude than if you are here. You see. This here is all. This is a resonance diagram. This is all the resonance, and this is the period of the resonance. Yeah. Nice. Okay. Nice. I want you to do some exercises in a moment, but I will talk just a little bit more. Have you guys internet already or not? No internet yet? You do. with IFT network. With EduROM, okay, with EduROM. But then few people have EduROM, right? No internet for people that don't have EduROM yet. Auditório. Auditório funciona. Auditório works. Okay, so everybody knows how to connect to Auditório. Auditório network, the password is this one. It's Jornada IFT 2000. It doesn't fit here. 2015. Okay. Everything together. Jornada IFT 2015. Okay. So this is the password for the Auditório network that apparently is working. Okay. Where did I send this out? Okay, people. So before exercises, I have a last thing that I want to show you. That sometimes you see, right? So I want you to now look at what happens if I want to vary two parameters at once. And then you say, well, isn't that too much? You already are varying one parameter over a whole range of values. Now I want you to do that with two, right? It looks, I don't know, do you think this is too much? Trust me, by the end of the week, you want to do this for 5, 6, 10 parameters at once, okay? Because, it's really hard to know parameters, so it's important to learn to explore this, okay? And this stuff is pretty much the same, okay? We want to change two parameters, for instance, in this model here. I think I'll go back to the SIRS model. And now I want to vary, for instance, beta and omega at the same time. Okay? At the same, of course, I can vary only beta and then only omega. But the point here is not varying one and then the other. No, vary both for all values of both. Okay? And to do this, it's pretty simple. We have to define once again a range of values for beta and a range of values for omega. Okay? Something like this. And now I have 20 values for beta, 24 values for omega, and I want to do all of them by all of the other, right? So this is 480 different combinations, yeah? Okay, how do I do this? What I do, I use this smart function here called mesh grid, okay? That makes a grid of values for both betas and omegas, okay? And this is what looks like for beta here, right? So this is, the grid looks like this. For every column, the value of beta is a constant, okay? And for every line, if I plot here, instead of B, I plot O, that is the omegas. Every line is a constant. You see, so each point in this grid has a different combination of beta and omega, okay? The betas vary along the columns, and the omegas vary along the lines. Yes? Okay. And now, what do? I do a double loop. A loop over the i's, over the b's, and over the o's. You see, so for these two values here, I would use bij, that is the value of beta for that value of I and j, and oij, that is the value of omega at that same point. Okay, and then what I use here is once again the final value of the infectious population, okay, the infectious prevalence, yes? And I save this into this array over here, okay? I think this calculation, my computer is so much better than Google's, okay? So it runs faster here, okay? And now what I'm plotting here is beta in the x-axis, omega in the y-axis, and in the color, this is a color plot. I'm plotting the proportion or the prevalence of infectious after a long time divided by total population, that is the small I, okay? And you see that for large beta, this is close to half. For small beta, beta close to 1, this is close to 0. And what is the dependence on omega? Almost no dependence on omega, right? So you see that if I fix a value of beta, along a single column here, the color is pretty much the same, yeah? Yeah, so what does that mean? It means that I actually didn't have to make this plot, right? Because the dependence on omega is negligible, yeah? Okay? So, but I learned something from doing this, okay? For any value of beta, the dependence on omega is negligible, yeah? Nice? At least if what I'm talking about is the endemic state, right? Maybe changing omega will change the values of the peaks, or it will change the frequency of those oscillations or other stuff like that. But for this thing here, it doesn't change, okay? And here this is just for fun. Instead of making a color plot, I could plot this in a 3G plot, okay? So this is a 3G plot, right? So I find it harder to look than the other one, right? But yeah, this is just for fun. And it's still just for fun. This is the solution with S, I, and R here. So I started here with S close to 1, I very small, and R equal to 0. And the solution goes like this. But again, not very useful, but this is just for fun. Okay. Okay. These questions about this. Does that make sense? The stuff with 2 parameters at once. Yeah. Okay. The issue is with 3 parameters, you cannot do this anymore. Okay. You cannot really visualize. This is already 3D, right? The 4th dimension here is the color. You cannot do this in another dimension. Okay, so you really have to work hard on restricting parameters in your models to only change, to fix as much as you can, to only change the ones you are actually interested in, right? Because you cannot really explore space of parameters with many free parameters. Okay. Questions?
How much is free?
What?
How much is many parameters free?
No, in a single analysis, you're pretty much restricted to 2, okay? Of course, do this 2 and then another 2 and then another 2, but you cannot plot 3 parameters, okay? It's already too much, yeah? Of course, you can do stuff that is like statistical analysis of sampling parameters from a distribution and so on, but this is so much harder, so much more complicated that sometimes it's harder to get information from this than than simply looking at more combinations of parameters. Okay.